Writing and maintaining tests is a tedious and error-prone process. Modern technology has come a long way to help automate parts of this process. In this lesson, we will learn about techniques for automated test generation. Since automated testing is impractical for entire systems, we will focus on techniques for automatically testing the functionality of the smallest testable parts of an application, called units. This approach, called unit testing, constitutes a software development process which is important in its own right. The techniques we will learn in this lesson are more directed compared to random testing. They observe how the program under test behaves on past tests in order to guide how to generate future tests. By being more directed, these techniques not only help find bugs more efficiently, but they also help to create a concise test suite that can be used for regression testing. Previously, we looked at random testing or fuzzing as a technique for testing. Recall that fuzzing is useful for finding possible security bugs as well as for testing mobile apps and multi-threaded programs. In this lesson, we will focus on more directed forms of testing rather than the purely random form of testing that is embodied in fuzzing. One such testing approach is systematic testing, embodied in a tool called Korat, which is suited for testing routines that manipulate linked data structures such as lists and trees. Then we will look at how we can combine the power of randomness and systematic testing, conceived in a tool called Randoop, which is suited for unit testing of Java program fragments like classes and libraries. These two directed forms of testing overcome a major limitation of purely random testing. They avoid generating illegal and redundant inputs that dominate the space of possible test inputs. Korat is a deterministic test generator which originated as a research project by a team of 3 graduate students at MIT. The idea behind Korat is to leverage the preconditions and postconditions of a function to automatically generate relevant tests for the function. How does it do this? We alluded to this problem previously in the course. There are potentially infinitely many tests we could run on a given piece of software, but we only have the ability to run a finite number of tests. And even if we restrict ourselves to tests of a finite size, the space of possible tests can become astronomically large very quickly. We need to choose a subset that is concise and diverse. By concise, we mean that it avoids 2 kinds of test inputs: illegal ones that do not exercise interesting functionality of the software, and redundant ones that exercise the same facet of the software. By diverse, we mean that it gives good coverage of the software, as measured by some number of code coverage metrics. One insight into automatic test creation can come from thinking about small test cases. In practice, we often do a good job of catching bugs by testing all inputs up to some small size. This can be expressed in what is called the small test case hypothesis. If there is any test that causes the program to fail, then there is a small such test. For example, if a list function works on lists of length 0, 1, 2, and 3, then it's likely to work on lists of all sizes. The intuition behind this is that such a function is typically written in a manner that is oblivious to the length of the list. For instance, it is unlikely for a programmer to write such a function with a giant switch statement for lists of lengths 1, 2, 3, 4, etc. Recall that we made a similar assumption with respect to bug depth in testing multi-threaded programs using fuzzing. If there is a concurrency bug in a program, there is usually one with small depth of size 1 or 2. Again, this led us to focus our testing on a smaller search space while maintaining good concurrency bug coverage. In order to systematically generate all test inputs up to a small size, Korat leverages knowledge of the type information of the input. For this reason, we would consider Korat a white box testing method. For instance, if we have a function that operates on a binary tree object, then Korat knows from the type of this object that it has a root field that points to a node object or null, and that each node object has 2 other fields, each of which points to a node object or null. Thus, to generate a set of small test inputs, Korat need only enumerate all possible shapes of binary tree objects that can be created from a fixed set Before we see how Korat enumerates such shapes, let's look at the scheme that Korat uses to represent different shapes uniformly. This scheme lies at the heart of how Korat systematically and efficiently enumerates the shapes. To represent shapes, Korat arbitrarily orders all possible values of each field, assigning each a unique ID, and it arbitrarily orders all fields into a vector. Each shape then is simply an assignment of values to fields in the vector. Let's look at a binary tree example to elucidate this concept. Suppose we wish to generate all possible binary trees of up to 3 nodes. Let's give unique identifiers n0, n1, and n2 to the 3 nodes. Then the vector of fields contains 7 elements, a field for the root of the tree and a field for the left and right child of each of the 3 nodes. Each of the boxes can contain either a null or n0 or n1 or n2. Each possible assignment of these values results in a different input shape to test. Let's do a quiz next to see how different assignments result in different shapes. This quiz is to ensure that you understand how these vectors, called candidate vectors, correspond to concrete representations of objects. Here are 2 possible shapes of binary tree objects. Fill in the boxes in the candidate vectors with the correct value for each field. Remember that you can also enter the word null into a field as appropriate. Now that we have seen how Korat represents each possible shape, let's look at how Korat enumerates them systematically. Here is the basic idea that Korat uses. The user selects a maximum input size, which we'll call k. Then Korat generates all possible shapes of size at most k. The precondition of the method under test is used to filter out invalid inputs. For example, we might not want to call a remove root method on an empty binary tree. Those test inputs that meet the precondition are run through the method being tested, and the results are checked against the method's post condition. This algorithm should be more or less familiar. The same basic flow happened with randomly generated test cases. The only difference is the way in which test cases are generated. Let's take a closer look at this. After all, how hard could it be to generate all binary trees with, say, 3 nodes? Why don't you take a shot at this question? Suppose we want to count how many possible shapes we could create by filling in the cells of a candidate vector. How many different candidate vectors are there? Fill in your answer in the box at the bottom. Let's generalize the setting in the quiz from binary trees using up to 3 nodes to binary trees using up to k nodes. Let's calculate how many binary trees we can make using up to k nodes. We have a single binary tree object bt and k node objects, which we will call n0, n1, n2, etc. There are 2k plus 1 node pointers to assign values to: the root field of the binary tree object and the left and right field of each of the k node objects. Also allowing a null pointer value, we have k plus 1 possible values for each node pointer, that is, each of the k node objects or null. Thus, we have k plus 1 to the power 2k plus 1 possible binary trees. You can verify the solution to the quiz by plugging in the value 3 for k in this expression. We get 4 to the power 7. That is 16,384 binary trees using up to 3 nodes. That's a lot of trees. This quantity grows super exponentially in k. For 3 nodes, we have over 16,000 possible binary trees that can be defined. For 4 nodes, we have nearly 2 million possible binary trees. And for 5 nodes, we have over 360 million possible binary trees. Clearly, this limits us to only very small test input sizes. Is there a way to do better? As you may have guessed, our count of k plus 1 to the power 2k plus 1 trees is a gross overestimate of the number of binary tree objects we'd really be interested in testing. Many of the structures that would be created by systematically filling in every possible value for left and right in the node objects would be disconnected or contain cycles and therefore would not be trees. Additionally, many of the trees that are created would be essentially the same. They would be isomorphic, indistinguishable for the purpose of testing. In fact, there are only 9 non-isomorphic binary trees using at most 3 nodes. One binary tree with a null root, one binary tree with a single node as the root and no children, 2 binary trees with a root and 1 child, one on the left and one on the right, 1 binary tree with a root and 2 children, and 4 binary trees with a root, 1 child of the root, and 1 grandchild of the root. To summarize, there are 2 central challenges: how to avoid generating illegal test inputs, which in this case are invalid trees, and how to avoid generating redundant test inputs, which in this case are isomorphic trees. These are challenges for any automated test generation technique, not only Korat. We will see shortly how Korat addresses these 2 challenges. We will also return to them in the context of another automated test generation technique later in this lesson. Let's focus on first effectively filtering out invalid trees. It's inefficient to generate each candidate input and then check whether it actually satisfies the conditions of being a tree. Instead, we want to avoid generating candidate inputs that don't satisfy the precondition in the first place. Let's look at how Korat uses the precondition as a guide in the generation of test inputs. The technique that Korat uses is to instrument the precondition. That is to say, it adds code to the precondition checking to observe how it acts on the test input. In particular, it records which fields of the input are accessed by the precondition. A key observation is that if the precondition never accesses a field of the test input, then the result of the precondition doesn't depend on that field. Let's take a look at the precondition for binary trees. For a data structure of this type to be a valid binary tree, it should satisfy one of 2 different cases. The root may be null, and if the root is not null, then the structure should be a directed tree. That is, it should have no cycles, every node except the root should have 1 parent, and the root should have no parent. Here is a concrete implementation of the precondition we just outlined for binary trees. It is a function called repOK in Korat terminology. It takes as input a binary tree object BT and returns true if it is a valid binary tree and false otherwise. In addition to this requirement, the repOK function must be careful not to access unnecessary fields of the binary tree object BT. Recall that Korat will monitor which fields this function accesses. So, the fewer fields that are accessed, the more Korat will be able to prune the space of candidate vectors that it considers. The repOK function starts out by checking whether the root is null. If so, it exits by returning true, since an empty binary tree is a valid one. If the root is non-null, the function uses a classic approach to traverse all the nodes reachable from the root and determine whether the resulting structure is indeed a tree. It uses 2 data structures for this purpose: a hash set that keeps track of all nodes visited so far, and a work list that keeps track of nodes that have themselves been visited but whose left and right children might not have been visited. While the work list hasn't been fully processed, the function removes the earliest node in the work list and checks whether its left child is non-null. If so, it then checks whether the left child has already been visited. If it has, then we have detected an invalid tree. In particular, we have detected more than one path from the root node to the current node, which violates the condition for a data structure to be a tree. If the left child wasn't previously visited, then we add it to the visited set and also to the work list. We then do a similar check for the right child of the current node. If both these checks succeed for all nodes that are reachable from the root, then the repOK function returns true, indicating that the input binary tree object represents a valid binary tree. Observe the order in which this function traverses nodes. This will be important in understanding how Korat systematically enumerates different shapes of binary trees. The order is depth first, left to right order. Let's look at an example to better understand this order. Suppose this binary tree object is input to the repOK function. We first visit the root field, which leads us to node N0. We next visit the left child of node N0, leading us to node N1. We then visit the left child of node n1, which is null. Notice that we went depth first, as far as possible to the left. When we cannot go left any further, we go right. So we next visit the right child of node n1, which leads us to node n2. We then visit the left child of node n2, which is null. So we then visit the right child of node n2, which is also null. When we cannot go right any further, we return to the parent node. In this case, we return to node n1. We are done visiting both the left and right children of n1, and so we return to its parent node n0. We already visited its left child, but not its right child. So we visit its right child, which is null. At this point, we are done visiting all left and right fields of all nodes reachable from the root field. Let's see how we can use the precondition we just saw for the purpose of test generation. Consider the following candidate input, which corresponds to the following binary tree object. Its root pointer is null, so there is no path to the node objects n0, n1 or n2 that were also generated in this input. For this input, the precondition only accesses the root field because it is null. The precondition therefore doesn't check any of the other fields. Indeed, any other shape for the remaining nodes would yield the same result, so there is no need to generate any other candidate input with a null root. This single input therefore eliminates 25% of the tests that would have been generated otherwise. The general procedure that Korat uses for generating tests is to enumerate the possible shapes by their associated vectors. The first vector generated is the vector with all null entries, corresponding to all fields being null. Then Korat checks that this shape satisfies the precondition. If so, then the shape is kept as a test case. Next, Korat expands the last field that was accessed while the precondition was checked. In other words, the field is assigned to the next object that could potentially be assigned to that field. Once all possible assignments for a field have been checked, then Korat backtracks in the following way. It resets that field to null, and then it expands the second to last field checked by the precondition. The key rule that lets Korat dramatically narrow its search space is that it never expands fields that are not examined by the precondition code. This is what allows Korat to skip all but one binary tree with a null root. The precondition code will stop at the root if the root is null, and so it won't assign objects to any of the other fields while the root is null. Additionally, by keeping track of which objects point to which types, Korat cleverly checks for whether it generates isomorphic and therefore redundant test cases, discarding any isomorphic test cases that it finds. For more details on the operation of the algorithm behind Korat, please see the paper linked in the instructor notes. This algorithm is a rather abstract manipulation of data structures. So let's take a look at how Korat would work in a concrete example to get a better idea of what it is doing. Let's see how Korat would generate test cases for a binary tree object with 3 nodes. Recall that the binary tree object itself has a root field that points to a node, and each node has a left and a right field that points to a node. Candidate vectors for test cases will consist of 7 cells, one for each of these 7 fields. We begin with all the cells in the candidate vector equal to null. This vector corresponds to the binary tree shape with a null root. We would then check that this shape passes the precondition for a binary tree object. While the precondition is running, let's write down the order in which the precondition code checks each field of the shape. Recall that the first line of the precondition code returns true if the root is null. Since the precondition returns true, we accept this object as a test case. Additionally, the precondition will inspect just the root field before it returns, and so the only field we will number is the root, which we number 1. Now we expand the last field that was checked, which will be the root field. By expanding, we increment the root field to the next object in the shape that is compatible with that field, which is a node object. Let's call the node objects n0, n1, and n2, and let's suppose that we'll increment in the order null, followed by n0, followed by n1, followed by n2. Now that we have expanded the root field, we have a shape consisting of the root pointing to a node which in turn has no children. Now we check that this shape passes the precondition code. The order in which the precondition accesses the fields is first the root, then the left child of the root, and then the right child. The precondition check will return true, and so we accept this shape as a new test case. Now, since n0.write is the last field that was checked by the precondition, we expand the n0.write field. This will result in n0.write changing from null to n0. But this shape contains a cycle, and so it will fail the precondition check for a binary tree object. Therefore, we discard this shape and expand n0.write again, assigning it the next node in our order, which is n1. This new shape is indeed a binary tree, and so it will pass the precondition check. Recall that the precondition code traverses the shape in a depth-first manner, choosing the left child before the right. So the ordering of field accesses will be 1, 2, 3, 4, and 5. We would then use this ordering to determine the field to expand for the next iteration. To check your understanding of the expand operation in Korat, fill in the candidate vectors for the next two shapes that Korat will generate. Omit any illegal shapes, that is, those that fail the precondition check, and any shapes that are isomorphic to any previously generated shapes. As a hint, here is the ordering in which the precondition checked each field of the last candidate vector. First the root, then n0.left, then n0.right, then n1.left, and finally n1.right. Let's do one more quiz to solidify your understanding of the Korat algorithm. Starting from where we left off in the previous quiz, enter the candidate vectors of the next two legal shapes that Korat generates. Remember to disregard any shapes that are isomorphic to a previously generated shape. As we have seen, with relatively few steps, Korat generates all the legal and isomorphically distinct test cases for binary trees with at most 3 nodes. In practice, Korat's scheme for eliminating illegal and redundant test cases have proven to be highly effective. Here you can see that for binary tree objects, for each node in the tree, the full state space grows by a factor of about 1000. But Korat is able to reduce its search space to about 4 times as many candidates considered for each additional node, a massive speedup. Similarly, for heap array objects, the state space grows by a factor of about 32 for each new node, whereas the number of candidates considered grows by only a factor of about 10. And for linked lists, the state space grows by a factor of 32,000 for each node, but the number of candidates considered by Korat only grows about 6-fold per new node. The time taken to run these tests is on the order of minutes or even seconds, so Korat could be easily included into regression tests to ensure that the code changes don't break previously established functionality. Let's wrap up our discussion about Korat by summarizing its strengths and weaknesses. Korat's test generation is at its best when we can easily enumerate all possibilities for the objects to be used in the test case. For example, if our test cases all involve 4 nodes and each node has 2 pointers to other nodes. More specifically, Korat is useful for testing linked data structures with small, easily specified procedures, such as emptying a stack or inserting an element into a heap. For this reason, Korat is a strong candidate for unit testing components of larger systems. Korat is weaker when it is harder to enumerate the set of all possible test cases. For example, the set of all integers, at least those representable in a 4-byte format on a computer, or the set of all single or double precision floating point numbers, or the set of all n-character strings with ASCII or Unicode characters. In these cases, while enumeration can be done in principle, even small test case sizes, such as 1 int, 1 double, or strings with 10 characters, lead to large numbers of test cases that Korat will not flag as isomorphic, because there are no links in the data to exploit in the culling process that occurs through precondition checking. We will see a different technique later in the course called dynamic symbolic execution that is capable of handling such data types. Another weakness of Korat is that it is only as good as the pre and post conditions that we specify for the methods being tested. In the example code presented here, we want to test a method that removes an element object X from a list object list. The precondition is that the element is a member of the list, and the post condition is that the element is no longer a member of the list. These are sufficient conditions to ensure that the remove method is functioning properly. If we are not as careful in our selection of pre and post conditions though, we may end up with many useless tests or even miss useful tests. Note that the precondition shown here, that the list object is not empty, is weaker than the earlier precondition that X be a member of the list. Whenever X is a member of the list will be non-empty. So we may end up with many useless tests that satisfy this weaker precondition but not the earlier precondition. Conversely, Korat might not expand the element X because it is not accessed during this precondition, resulting in missing useful tests. In other words, there may be bugs in this method that are dependent on the value of X that wouldn't be found by Korat using this precondition. Likewise, checking that the output of the remove method is still a list is weaker than the earlier post condition, which stated that the output is a list that no longer contains X. Since this post condition does not check that the list no longer contains X, it will silently succeed if the remove method has a bug that fails to remove X from the list while still preserving the list structure. We will now switch to a different test generation technique called feedback-directed random testing, which was first conceived in a tool called Randoop, which stands for Random Tester for Object-Oriented Programs. While the deterministic test generation that Korat performs is better suited for generating different shapes of a data structure, Randoop is better suited for creating different sequences of methods in an object-oriented library that provides an application programmer interface, or API. This is not to say that one technique is better than another in testing. In fact, they are complementary to each other. For instance, automatically testing a linked list implementation in a robust manner would require not only generating lists of different sizes, but also generating different sequences of list operations. Let's look at a concrete example that involves testing the API of various container classes in Java Standard Library, such as linked list and tree set. Here is a real unit test generated by Randoop when run on the Java Standard Library version 1.5. This test shows a violation of the equals contract. A set S1 returned by the unmodifiable set library method is not deemed equal to itself, which violates the reflexivity property of the equals method as specified in the Java Standard Library API's documentation. This test actually reveals two errors, one in the equals method and another in the tree set constructor method, which failed to throw a class cast exception as required by its specification. Formally speaking, Randoop generates object-oriented unit tests consisting of a sequence of method calls that set up state, such as creating and mutating objects, followed by an assertion about the result of the final call. How does Randoop generate such tests? Let's take a look. In this setting, a test is a sequence of public library methods that an application using the library can call. While uniform random testing was suitable for the applications in the previous lesson, such as security testing and testing of entire systems like mobile apps or concurrent programs, here we want to generate a concise yet diverse test suite for testing a library. A major problem with the uniform random testing approach here is that it would create too many illegal and redundant method sequences. We will see examples of such sequences shortly. This motivates Randoop's variant of random testing called feedback-directed random testing, in which each new test is guided by feedback from running previously created tests. In what follows, we will use the terms test and method sequence interchangeably. Randoop uses the following recipe. It builds new method sequences incrementally by extending past method sequences. As soon as a method sequence is created, it executes the sequence. It then uses the result of this execution to determine whether it is an illegal or a redundant sequence, in which case it discards the sequence. Otherwise, it remembers the sequence to extend it when generating future sequences. Let's begin by looking at Randoop's input and output. Randoop's input consists of three things: a set of classes making up the library under test, a time limit that allows the user to control how many tests Randoop generates, and a set of contracts, which are properties that the object generated in the final call of a Randoop generated test is required to satisfy. Generally, these properties are specified in the library API's documentation. An example contract that must hold for any Java object O is that calling the hashcode method on it does not throw any exception. Another example contract is that using the equals method to test any Java object O's equality to itself must always return true. While these are generic contracts defined by the java.lang.object class, which is the parent class of all Java objects, one can also provide class-specific contracts for Randoop to check. Randoop's output consists of contract-violating test cases. It consists of two parts: a sequence of calls to public methods in the input classes, which set up state, such as creating and mutating objects, and a contract, stated as an assertion about the result of the final call in the sequence, in this case S1. In order for this test case to be valid, two conditions must hold. First, no contract should be violated up to the end of the execution of the sequence. For instance, no exception should be thrown during the execution of the sequence. Second, the final assertion should fail when executed. These two conditions will be important in deciding what Randoop does with each test case it generates, whether it discards the test case, whether it outputs the test case, or whether it retains the test case for extending in future test cases. Now that we have looked at the input and output of Randoop, let's look at the algorithm underlying Randoop. Throughout, the algorithm maintains a set of components. Each component is a sequence of code statements that computes values for arguments of the methods that Randoop decides to call in the sequence it generates. This set of components starts out with singleton sequences called seed components. For example, we have shown two seed components here. If Randoop decides to call a method with an integer typed argument, it can use this first component, which computes the integer I. If Randoop decides to call a method with a Boolean typed argument, it can use this second component, which computes the Boolean B, and so on. This set of components grows with progressively longer sequences as the algorithm progresses. These sequences will compute increasingly complex objects such as linked lists and trees. Next, the algorithm repeats the following process until the specified time limit expires. It first creates a new sequence of method calls. For this purpose, it does three things in order. First, it randomly picks a public method from the input classes to call. Let's say this method is named M, and that it has n arguments t1 through tn, and that it returns a result of type tret. M is the final method that the algorithm will call in the sequence that it is building. Calling this method alone will result in an invalid test case that might not even compile. In particular, the algorithm must assign a type-compatible value to each of the n arguments before calling this method. For each argument of type ti, Randoop randomly picks a sequence si already generated from the components that constructs an object vi of that type. Finally, it assembles the n randomly picked sequences, one for each of the n arguments, into a new sequence and appends the chosen method m at the end of that sequence. This becomes a new sequence denoted as new. Just like each of the subsequences S1 through Sn produced a result stored in variables v1 through vn respectively, the new sequence snew produces a result that is stored in variable vnew. Once a new sequence is created, the algorithm has three options to dispose of the sequence. It can discard the sequence, or it can output the sequence as a test, or it can add the sequence to the set of components. The third option is what allows the algorithm to produce increasingly richer method sequences over time. Each new method sequence that is added to the components itself becomes available for extension in future method sequences that the algorithm generates. Let's look next at how Randoop decides how to classify each sequence. Randoop uses the following decision process to classify each sequence that it creates in the algorithm we just saw. It executes the sequence and makes 3 checks on the result. The first check determines whether the sequence is illegal. Intuitively, a sequence is illegal if it violates a precondition. For example, if an exception is thrown during the execution of the sequence. If so, the sequence is discarded. Otherwise, it checks whether the sequence violates a contract. Recall that a contract is analogous to a post condition, an assertion on the final result of the sequence. If a contract is violated, it outputs the sequence as a contract violating test case. Otherwise, it checks whether the sequence is redundant. If so, it discards the sequence. Otherwise, it adds the sequence to the set of components. The first 2 checks ensure that such a sequence does not violate any precondition or any post-condition. There is no point in extending such a sequence further. The third check ensures that such a sequence results in a program state that has not been seen before. It is not necessary to extend such a sequence further, as its effect has already been captured by some other sequence already in the set of components. Let's elaborate a bit more on how Randoop decides whether a sequence is illegal and whether a sequence is redundant. An illegal sequence is one that crashes before the contract at the end of the sequence is checked, for example, by throwing an exception. Intuitively, an illegal sequence is one which violates some precondition during execution. Note that this concept of an illegal sequence is analogous to the concept of an invalid shape in Korat. If a shape generated by Korat violates the precondition, then that shape is considered invalid. Here is an example of an illegal sequence. In this test case generated by Randoop, the contract d.equals_d is not even reached because the call to setMonth throws an exception. The reason is that a precondition of the setMonth method is that the argument I denoting a month must be non-negative, whereas in this test case, it is -1. As an aside, you might be wondering how Randoop generates arguments like 2006, 2, and 14 used in the call to dates constructor method. The answer is that the set of seed components in Randoop is highly configurable. It allows a wide range of possible constants. Randoop uses a simple heuristic to decide whether a sequence is redundant. It maintains the set of all objects created in the execution of each sequence. A new sequence is considered redundant if each object created during its execution belongs to this set. Randoop uses the equals method to do this comparison check for each object. Let's look at an example. Consider this sequence which creates a hash set and adds a single element, the string hi, to it. Suppose we then extend this sequence with a call to s.isEmpty. Is this new sequence redundant compared to this sequence? The answer, according to Randoop, is yes, because the equals method states that the set object s in this new sequence is logically equivalent to the set object s in this old sequence. This is not a foolproof comparison. On one hand, this comparison may mistakenly deem a new object as equal to a previously created object, causing Randoop to conclude that a sequence is redundant and thereby miss bugs that can be triggered only by extending that sequence. On the other hand, this comparison may mistakenly deem a new object as not equal to a previously created object, causing Randoop to conclude that a sequence is not redundant. While this case is less problematic in that it at least won't cause Randoop to miss bugs, it does bloat the set of components and reduces the chance of creating new object states in future sequences. Nevertheless, Randoop's heuristic works well in practice, and it can be disabled or refined by the user. For instance, it is straightforward to use reflection to write a method that determines whether two objects have the same concrete representation. that is, the same values for all their fields. Or the user can specify more sophisticated methods to determine state equivalence. The authors of Randoop applied the tool to three large libraries: the Java Standard Library, or the JDK, the Apache Commons collection of reusable components, and Microsoft's .NET framework. Randoop discovered previously unknown errors in all three libraries. Let's take a look at some of these errors. In the JDK's containers library, which includes facilities to create containers such as lists, trees, etc., Randoop found 4 methods that violate the reflexivity property of the equals method. Randoop also found that the JDK's XML library can create objects that cause the hashcode and toString methods to crash, even though these objects are well-formed XML constructs. In the Apache libraries, Randoop revealed constructors that leave fields uninitialized, leading to null pointer exceptions on calls to equals, hashcode, and toString methods. Randoop also found many errors in the .NET framework. This includes at least 175 methods that throw an exception forbidden by the library specification, such as a null pointer exception, an array out of bounds exception, or an illegal state exception. Randoop also discovered 8 methods in the .NET framework that violate the reflexivity property of the equals method. You can learn more about Randoop by reading a technical paper linked from the instructor notes. Now let's do a few quizzes so you can check your understanding of the Randoop algorithm. For this quiz, let's look at the binary tree class we considered earlier for Korat. This time, our API consists of 3 methods: a constructor for the binary tree class, which takes as an argument a single node which becomes its root, a remove root method for the binary tree class, which takes no arguments and returns a node object, and a constructor for the node class that takes 2 nodes, which will become the left and right children of the newly created node. Note that the binary tree constructor has an assert statement that ensures that the binary tree object being created is a valid representation of a binary tree. It uses the rep_ok method we saw earlier for this purpose. Also note that the remove root method has an assert statement which requires that the root of the binary tree be not null. For the quiz, write the smallest possible Randoop sequence creating a valid binary tree object. Then decide how Randoop will classify the sequence. Will it discard the sequence as illegal, or output the sequence as a bug, or add the sequence to the set of components for future extension? Next, write the smallest sequence that Randoop can generate, which will violate the assertion in the remove root method. Then decide how Randoop will classify the sequence generated. Now, what's the smallest sequence Randoop can generate which will violate the assertion in the binary tree constructor method? The code for the rep_ok method is given in the instructor notes if you need it as a reference. After writing the sequence here, answer the following question. Is it possible for Randoop to create a binary tree object with a directed cycle using the given API? As we begin to wrap up this lesson, let's take a moment to compare and contrast the 2 tools we have seen for automated test generation. Identify which of the following statements are true for each of Korat and Randoop by checking the appropriate boxes. Which of the techniques uses type information to guide test generation? Which of the techniques generates new tests fully independently of past tests? Which of the techniques generates tests deterministically? Which of the techniques is suited to test sequences of methods? And which of the techniques avoids generating redundant tests? In this lesson, you have learnt about 2 powerful test generation techniques in detail. Before we conclude, let's take a moment to step back and look at the bigger picture of test generation. One question that you may have considered in this lesson is, both Korat and Randoop were tools invented in the 2000s. But why didn't automatic test generation become popular decades ago? The most prominent reason for this delay is that earlier programming languages had weak type systems, whereas automated techniques rely heavily on type information. Earlier languages such as C and Lisp just did not provide the needed types. Contemporary, strongly typed languages such as Java and UML lend themselves better to test generation because automated tools can exploit type information to eliminate illegal and redundant test cases and effectively prune the space of candidate tests. Let's wrap up with a summary of what we learned in this lesson. Automatic test generation is a good idea. It helps find bugs quickly and it does not require writing or maintaining tests. The key to making it work efficiently is to avoid generating illegal and redundant tests. If one is not careful, these kinds of tests dominate the test generation process and make it ineffective. Even better, automatic test generation is possible to do today, at least for small units of a software system, such as a data structure or a library API that is written in a strongly typed language like Java. Finally, automatic test generation is being adopted in industry and is likely to become widespread in future, especially in targeting specific kinds of bugs, such as security bugs or concurrency bugs, and specific classes of programs, such as mobile apps or device drivers.